Okay, so the first spatial talk, I'm gonna introduce the coating methods to strengthen the commercial carbon fiber. Okay, the ceramic coating to strengthen the commercial carbon fiber. Okay, and we know that a carbon fiber has been widely used in different industries, such as the aerospace or the automobile industry. Well, its characteristics are can enhance the component strength, and also it has the high stiffness, and it has the low density to reduce the weight of the whole components or products. Okay. However, for some like the environmental issues, some air pollution is gonna produce uh, some acid gas, and those can accelerate the corrosion of those carbon fibers. Okay, and also we would like to ceramic coated those fibers to replace the Kevlar fiber. Okay, so whether we can replace the Kevlar fiber by using the ceramic coating on some commercial carbon fiber. Okay, that's the key point that we're gonna discuss in this spatial talk. Okay. Okay, therefore, it can be improved by surface treatment, not only to change its surface property, but also to strengthen its mechanical property, right? And by ceramic coating, which has the good mechanical property, thermal stability, chemical stability, and so on, and so on. Okay, therefore, this ceramic coating can be regarded as the surface protection coating. Okay, and I'm gonna introduce you the key materials, the raw materials called the PDC, polymer derived ceramics. Okay, polymer derived ceramics. Okay, the most commonly used the pre-ceramic precursor backbone is based on silicon and adjusted the molecular level with two important parameters. Okay, the functional group X on the polymer backbone and the substitute R1 and R2 connected to silicon. Okay, so we can look at this figure. We can look at this figure. It shows the different. It's kind of a structure of PDC. Okay, structure of PDC. If this X, I already mentioned that X group, the silicon connect to X equals to oxygen, the X as oxygen. Okay, and after pyrolysis, the ceramic film and its structure as silicon oxycarbide. Okay, therefore we saw it's silicon oxygen bond. Okay, and if the silicon atom connected to a carbon atom, okay, so it's based on silicon and carbon bond. After pyrolysis, the silicon carbide ceramic film. Okay, and if the functional group is nitrogen, so it's a silicon nitrogen bond, and after pyrolysis, the silicon carbon nitride ceramics film. Okay, and its pre-ceramic precursor is polysilazane. Okay, this is what we use in this spatial talk. Okay, and because this pre-ceramics precursor is liquefies, okay, in the beginning it's liquefies, therefore it can incorporate with different metal or ceramic powder. Okay, and due to its liquid property, it's easy to manufacture, right? Because it's raw materials is a liquid. It's a polymer, liquidic polymer. Okay, therefore, I mean, some processing techniques, like injection molding, casting, and pressing, and spray coating, and so on. Well, it's quite easy to fabricate it via those commercial manufacturing process. Okay. Okay, what's the temperature effect? What's the temperature effect to the transformation of preceramic precursor? Okay, so at low temperature, I mean from the room temperature to maybe 100 or 200 Celsius, it can solidifies. That means shaping. We can use the casting process. We can make a mold, and we can put this liquid polymer into this mold. Just put it in the air environment. Okay, after a few days, and this polymer will be cured, or we can say it's be cross-linked at low temperature. Okay, and if you want to facilitate its cross-linking process, you can heat treat it at an elevated temperature between a few hundred Celsius, maybe below 400 Celsius. Okay, it's a cross-linking temperature. When this temperature, this heat treatment temperature is higher than 400 or even higher, and this process becomes pyrolysis. Okay, pyrolysis. Okay, from few hundred to 1400 Celsius. Okay, during this pyrolysis, its structure, its PDC structure is still amorphous. Okay, it's still amorphous. Oh, well, it depends on what kind of structure, what kind of bond. As I already mentioned previous slide, it's silicon oxygen or silicon carbon or silicon nitrogen bond for those preceramic precursor. Okay, and when this heat temperature or this pyrolytic temperature is higher than 1400 Celsius, and this kind of precursor start to crystallize, start to become more crystallization. Okay, become more crystallization. Therefore, this very interesting materials is that you can control its property or its structure by temperature. Well, it can be a polymer phase or the ceramic phase. It can be amorphous or crystalline. It totally depends on the pyrolytic temperature. Okay, pyrolytic temperature. Okay, and this kind of materials has been widely used in different industries, such as the ceramic glow plug, or the brake disc, or the pressure sensor, or gas sensor, or it has been used some defense industry for the ceramic protection layer. Okay. Okay, so what's our experimental methods in this spatial talk? Okay, first we just cut this fiber, carbon fiber, from the Formosa plastics. Okay, we just fix the length about 8 centimeter. Okay, and we spray coating. We spray this pre-ceramics precursor. Okay, and it's silicon nitrogen bond. It's polysilazane. Okay, it's pre-ceramic precursor. Just sprayed it, and we just put this this sprayed carbon fiber into a vacuum oven. Okay, and preheat it at 150 Celsius for an hour. Okay, and this carbon fiber has been this spray coated carbon fiber has been partially cured. Okay, partially cured. And this partially cured fiber is pyrolyzed in a tubular furnace under the inner gas. Okay, to achieve the temperature that you want. Okay, so and also we add the graphene into this carbon fiber, spray coated carbon fiber. Okay, therefore the fiber with the ceramic coating without graphene, we call it ceramic based carbon fiber composite. And if the ceramic based carbon fiber is incorporated with graphene, it's called the graphene-reinforced carbon graphene-reinforced ceramic fiber composite. Okay, it's a GRCFC and CCFC. Okay, this G means graphene. Okay, this G means graphene. Okay. Okay, so this is our experimental parameters. We just adjust the concentration, just dilute this polysilazane preceramic precursor in acetone. Okay, so it's mean the 20% of the polymer, the preceramic precursor, and 80% of the acetone. Okay, and we use this abbreviation represents the 20% weight percent of preceramic precursor, and so on. Okay, and this means that the 40% of the preceramic precursor and the 60% of acetone. Okay, and also we use the G define the content of graphene. Content of graphene. The 0.1 means 0.1 weight percent graphene inside this CCFC. Okay, inside this composite with 20% preceramic precursor. Okay, and so on. So we have different content of graphene, 0.1, 0.2, 0.3, 0.4, 0.5, and so on. Okay, and so on. Okay, and this is our heat treatment process. Okay, so we have the different, it's called the final temperature of the 750, 650, and 550, and so on, which is heat treated at a different product temperature. Okay, so we spray coated this polysilazane precursor on this commercial carbon fiber, and we heat treat it at different product temperature. Okay, so this is our sample. It's already coated. Okay, so this is the CCFC or the GRCFC. Okay, and we use the glass fiber board to glue. Okay, to fix, to prevent from the slipping during the tensile testing. During the tensile test. Okay. Okay, and then we work on this called the corrosion test by the electrochemistry test. Use the 3 electrode method. Okay, we have the working electrode, that's our fiber. Okay, and the counter electrode is platinum, and the reference electrode is AgCl, and the electrolytic solution, the electrolyte is 0.5 m sulfuric acid. Okay, and we also do the Chronoamperometry test. Okay, that's mean we just fix this applied potential, and we measure its current with time. Okay. Okay, let's look at the result. What's the result we have? First, this is the SEM image of the coated carbon fiber. Okay, the ceramic coated carbon fiber. Okay, so the figure A shows the pure fiber, and its diameter is about 8 micron. Okay, 8 micron, and after coated this preceramic precursor polysilazane, and he treated at 350. So you can see this fiber is fully covered by this preceramic precursor, right? And we have these images with different periodic temperature. It's 350 and 450 and 750. So it's obviously can be observed that when this fiber, this coated fiber, pyrolyzed at high temperature, in this case it's a 750. the crack foam. Okay, the crack right here is the crack, is the crack, is the crack, 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 crack. And also this coating is delaminated from the fiber. Okay, delaminated from the fiber. Okay. So you can see the crack foam. Okay, the crack foam. Okay, so let's look at the tensile test result with different periodic temperature of this CCFC. So what's this figure tell us? So we have this figure shows the tensile test versus the concentration of polysilazane precursor. Okay, so obviously the ultimate tensile stress is enhanced. Is enhanced at specific concentration and the specific periodic temperature. Okay, therefore, at this point, and this point is for the pure fiber without any coating. Without any coating. We have the 20, when we coated 20% preceramic precursor on commercial carbon fiber and pyrolyzed at 450 Celsius, you see the UTS, the ultimate tensile stress, enhanced, partially enhanced, slightly enhanced. Okay, and when this concentration increased to 40%, that's the highest UTS of the CCFC, right? CCFC. I mean, this point is higher than the pure carbon fiber. Okay, it's higher than the pure carbon fiber. Okay, however, when we use the pure polysilazane preceramic precursor, its UTS, its ultimate tensile stress drop, which is lower than that of the pure carbon fiber, right? You see here. Okay, therefore we can have a summary that the periodic temperature, the optimal periodic temperature is at 450 Celsius. Okay, with the 40% of the polysilazane preceramic precursor. Okay, and it's about the 15% enhancement of the tensile strength, Okay, and also we compare with the CCFC incorporated with graphene content. So what this figure tells us? This graphene content is enhance the tensile stress when it is about 0.5 weight%, right? Right here. Okay, it's the pure carbon fiber, okay, without any coating. And this is a carbon fiber with the preceramic coating without any graphene content. Okay. Okay. And when this content, the graphene contents reach 0.5%, it has the highest tensile stress. Okay. And while the similar result is that when this periodic temperature increase and this tensile stress decrease, right here. Okay. So therefore, we can have a conclusion about this effect of graphene content with tensile stress. Okay, so we can find the highest tensile stress enhancement by the graphene. It's about 0.5. Okay, Okay, when this graphene content higher than 0.5 weight%, its tensile stress drop suddenly. Okay, drop. Okay. So the enhancement of the tensile stress is about 26% via graphene content at 0.5 weight%. Okay. Also, let's look at the Young's modulus. Okay, Young's modulus. You see, well, the Young's modulus, well, basically is decreased. Okay, its trend is decreased. And only when this concentration of preceramic precursor at 20 and 40 weight% is enhanced. Okay, pyrolyzed at the 750 Celsius. Okay, otherwise those Young's modulus are decreased compared with the pure fiber. Okay, compared with the pure fiber. Okay, so therefore it's interesting that the Young's modulus decreased about 7.8% at the product temperature 450. Okay. Okay. So controversial. I mean, the previous we are discussing about the tensile stress enhance, the highest tensile stress enhancements are at 450 Celsius, right? And the highest decrease of the Young's modulus is also at 450 Celsius. Okay, because at this temperature, while this preceramic precursor is not completely, or it just cross-linked, well, it's still a polymer phase. Okay, therefore, maybe its toughness is higher than that pyrolyzed at a higher temperature, right? You have a higher toughness. Well, this higher toughness, it has this UTS. Okay, however, for Young's modulus, usually the higher toughness has the lower stiffness. Well, we can say a higher toughness has the lower Young's modulus. Okay. Okay, so let's look at whether this graphene content can enhance or increase or decrease the Young's modulus. We see, well, the similar result shows that when this graphene content is about 0.5 weight%, the Young's modulus is increased. Okay, it's increased. And we just try the different weight% of graphene content. Okay, graphene content. Okay, and we figure out that when this graphene content is about 0.3 weight%, 0.3%, it has the highest Young's modulus. I mean, this carbon fiber composite has the highest Young's modulus. Okay, and the enhancement of Young's modulus is about 26% by graphene, by this graphene. Okay. Okay, so what's the specific strengths? That means we the tensile stress is divided by the specific density. Okay, the tensile stress divided by the specific density. Okay, therefore, so we figure out that when this carbon fiber composite is incorporated 40% of preceramic precursor and pyrolyzed at 450, its specific strength is enhanced about almost 40%. Okay, so the highest specific strength means that this composite, this fiber composite, has the highest strength with low density. That means the light. Okay, its weight is light with the highest strength. Okay, and also compare of the specific strength with graphene content. Okay, graphene content. You can see the graphene content extremely enhance the specific strength. Okay, this is the pure fiber. Okay, this is the zero without any graphene, and it's 0.5 graphene. Okay, therefore the graphene content is about 0.5 weight%. That's the highest specific strength. Okay, and what's the highest tensile stress with graphene content? 0.3, right? In the previous slide, I show you that where this graphene content is about 0.3 weight%, and its specific, its tensile stress is the highest. Okay, it's the highest. Okay, and this enhancement of specific strength is about 73% by graphene content. Okay. Okay, also we compare with the specific modulus. It's the same. We just use the Young's modulus divided by the specific density. Well, the trend is decreasing. Okay, the trend is decreasing. Okay. Okay, so let's look at the spec modulus of the graphene content, and also when this graphene content is about 0.3 weight%, yes, the highest specific modulus. Well, usually the incorporation with graphene as a function to enhance the specific modulus. Okay, so no matter what's the concentration, well, it's still higher than the pure carbon fiber or this preceramic coated carbon fiber. Okay. So the highest enhancement of specific modulus is about 61% at 0.3 weight% of graphene content. Okay. And we can have a summary table of the mechanical properties. For the pure carbon fiber, its tensile stress is about the 1080 megapascal, and with and this carbon fiber coated with 40% polysilazane preceramic precursor and pyrolyzed at 450. Its tensile stress is enhanced about 15%. And when this carbon fiber coated with 20% of the preceramic precursor with 0.3% of graphene, and as tensile stress is enhanced about 14.5%. Okay, and when it incorporates with 0.5 weight% of graphene, its tensile stress is enhanced about 26%. Okay, and for Young's modulus, it's decreased at 40% of preceramic precursor pyrolyzed at 450. Okay, because this polymer phase is not fully transferred. Well, it's partially cured at the 400 something. Well, however, this as composite incorporates with 0.3% of graphene, and as Young's modulus enhanced 26%. With 0.3, well, It enhances only about 2.6%. Okay, and this specific strength is enhanced about almost 40% by graphene content, and it's about 46% by graphene content, and 73%. Okay, this specific strength is enhanced about 73% with 0.5% of graphene content. Okay, and also the specific strength, specific modulus. Okay, is enhanced by the graphene content. Okay, so there's only one number is decrease. Okay, and only one number is decrease here. Okay, so we work on the Tafel curve. Okay, we do the Tafel curve experiment to represent the anti-corrosion ability of this CCFC or GRCFC. Okay, so the result shows that this is the pure, right? Pure carbon fiber, and this region shows the it shows the preceramic coated and pyrolyzed at 450 Celsius. Right. So what's the result tell us? You see, it's corrosion potential, maybe right here, right? Right. It's much higher than the pure carbon fiber, and its corrosion current is much lower. It's much lower than the commercial fiber. Okay, what's that mean? That means, well, the CCFC, that's mean the polysilazane precursor coated carbon fiber, has very good anti-corrosion ability. Okay, and we can calculate its polarization resistance and the corrosion rate. Okay, you see after coating with different concentration of the preceramic precursor, its corrosion rate is stable and much lower than the pure fiber. Okay, pure fiber. And the same result shows with the GRCFC, graphene content, okay, carbon fiber, has the same result as that of the CCFC. Okay, and we compare with other metal alloy. So we have the lowest three, our studies. Okay, our studies right here. It's much lower than the three reference. Of course, it's much lower than some metal coating or the high entropy alloy coating. Okay. And we also do the Chronoamperometry test. We work on the fixed potential, a fixed applied potential, and we measure its current change with time. Okay, current with time. So what do we get here? This is the pure carbon fiber. Okay, in the 0.5 m sulfuric acid, and this is the coating. It's the coating of the 40% of the preceramic precursor and pyrolyzed at 450. Right, which is enlarge the scale. You can see it's quite stable. Okay, you have to enlarge the scale. Okay, it's quite stable. Okay, this one is stable. This one is unstable. Okay, and this shows the graphene content. Right here is graphene content. There's different graphene content. Okay. So just enlarge this region to here. So the conclusions. So with the CCFC, that is the we have the 48% of preceramic precursor coated on commercial carbon fiber and pyrolyzed at 450 Celsius. And the specific strength is enhanced about 40%, and the specific modulus is enhanced about 15%. Okay, 15%. And for the GRCFC, that's mean the graphene incorporated. Okay. For this carbon fiber coated with 20% of polysilazane and incorporated with 0.5% of graphene. Okay, and the specific strength is enhanced about 73%. Okay, and the specific modulus is enhanced about 40%. Okay. Okay, of course, the corrosion, the anti-corrosion test showed that the CCFC has the higher corrosion potential, right? This is the corrosion potential for the pure carbon fiber, and this is for the coated carbon fiber. Okay, and this corrosion rate for this coated is much lower than that of the pure carbon fiber. Okay, it's pure. And through this graphene incorporated carbon fiber, well, its corrosion potential is similar to that of the CCFC. Okay, it's similar to that of CCFC. It shows that this polysilazane preceramic precursor has the high anti-corrosion ability. Okay, and we already know graphene is easy to oxidize in strong acid, right? In strong acid. However, when this graphene incorporated carbon fiber has the ceramic coating or has the this preceramic coating, well, its corrosion potential and its corrosion current density and corrosion rate is quite similar to that of the CCFC. Okay, so this is our first spatial talk today. Well, I just want to give you an idea of polymer derived ceramics, which has the function for protection. Well, it has the high mechanical strength and the anti-corrosion ability, and it is easy to fabricate. Well, you can coating by different manufacturing process, different metals or different ceramics, and so on. Okay, so this work has been published, so I will provide the link, okay, below. And if you want to read this whole journal paper, well, just refer to it. Okay, thank you today.